All right, it is 10 a.m. on the dot, so we're going to get started with this morning's field trip. Welcome, fourth graders, to the Dallas Independent School District STEM Environmental Education Center. We'd like to give a special welcome to the fourth graders at Martha Turner Riley Elementary, Spicewood Park Elementary, and Southwest ISD, the fourth graders at Hotchkiss Elementary, and the fourth graders at the Solar Preparatory School for Girls. Thank you so much for joining us today. We wish you could be here in person, but we're going to do our best to make you feel like you're here through this virtual field trip. If you are watching this and you have not registered yet for this field trip, you can still do that by going to www.tiny.cc/EEC register to get yourself or your class registered for this field trip. We just use that information for our attendance purposes. Today's virtual field trip is going to be all about forms of energy. So during this virtual field trip, students will differentiate among forms of energy, differentiate between conductors and insulators of thermal and electrical energy, and observe that electricity travels in a closed path, creating an electrical circuit. We're going to start off by exploring mechanical and thermal energy. Then we will explore light and sound energy. Next, we'll explore conductors and insulators. And last, you're going to see how an electric circuit works. While we're doing all of that, you can ask us questions, but since this is a virtual field trip, you can't just raise your hand and be called on. Instead, you'll go to a website, which is www.tiny.cc/EEC-question-answer. And there you can fill out a very short form and type in any questions you have related to forms of energy for us. You can ask as many questions as you like, and we'll do our best to answer all of them in the time that we have with you this morning. So let me stop sharing my screen here, and we'll get started with the field trip. We're going to start off by differentiating between mechanical and thermal energy with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be looking at mechanical and thermal energy. So we're going to go ahead and start off with mechanical energy first. So mechanical energy is simply the energy that an object has due to its position and also due to its motion. And there are two words that we typically refer to when we talk about mechanical energy, and that is potential energy and also kinetic energy. So let's start with potential energy. So potential energy is just the energy an object has due to its position. So let's take a look at what I mean by potential energy. So you guys are probably familiar with inclined planes. And here's an example of an inclined plane or ramp. And if I have this little car, I put it at the top of my ramp. So this car has potential energy. It has potential gravitational energy. So it has the potential to possibly do work. Now, if I push it down the ramp, it's going to have kinetic energy. And kinetic energy is just the energy of motion. So whenever things move, they have kinetic energy. So I'm going to go ahead and push it down the ramp, and that represents the kinetic energy. So again, this was just an inclined plane. It's an example of a simple machine. So the easy way that I remember it, I learned this from a coworker, and that is please kick me. So please stands for potential energy. K stands for kinetic energy, and when you add the sum of the potential energy plus the kinetic energy, you get an object's mechanical energy. So that's what those words mean. So our next few examples, we're going to take a look at some examples of toys that you guys are probably familiar with that utilize mechanical energy. So let me kind of get all my stuff in front of us. So the first thing that you guys are probably familiar with, we have another car. It already went off. That was on a spring-loaded little device here. And when I pressed the button, the car just went off. We have another little toy here. There's a wind-up spring. That spring has stored elastic energy, so that's the potential energy. And then when I release it, the bird then has kinetic energy, energy of motion. And then you guys are also familiar with, doesn't want to stop moving. Then you guys are also familiar with mechanical sharpeners. So we actually have to exert work. We have to do work to make our mechanical sharpener work. Same thing with the mechanical pencils. They get that name because we are doing work to make the pencil lead come out so that we can write. Now let's take a look at this fun toy. This shows us an example of lots of other forms of energy as well. Oh, it's not going to work right now. So this one, when I press the button, there it goes. When I press the button, we have kinetic energy. So we have the motion of the string moving around in a circle. We also have light energy. We can see the light, and then we also have sound energy as well. We can hear the sounds that it's making. And then another toy that we have that you guys are familiar with, slinkies. So when they're in motion, they have kinetic energy. And then here's a little handheld flashlight. We add mechanical energy to it by shaking it, and then there's a capacitor inside that stores that energy and converts it into electrical energy so that the flashlight will turn on. So it's important to note that energy is simply being converted. So we're not just creating new forms of energy out of thin air. It's being converted from another form of energy. So that's kinetic energy. And I have one last example of kinetic energy that we're going to look at. So these are some cool little sticky ninjas. If I throw them at the board behind me, you're going to see that they start off with potential energy. And then as they start moving, that is the kinetic energy. And it might take some time. Some of those were some bad throws, but you can see that they're starting to move. So that's the kinetic energy. Another last example of kinetic energy, if you're in DISD, you can check out a lot of cool science equipment for free. Here's an example that you can check out. It's a marble launcher. You can stick some spheres inside. There's a spring, and then you can experiment with the different angles and then the different tensions to see how far you can get the marble to launch. So I'm just going to do a quick example. I'm not going to launch it very far since I'm in my classroom, but we're just going to do it at the lowest spring level, and then we'll go ahead and see what it does. I know because of the view, you won't be able to see how far it goes, but you should be able to see it take off, and that happens really quick. But again, lots of cool things that you guys can check out for free if you're with DISD. The next thing we're going to take a look at, that was mechanical energy, and that's just the energy an object has due to its position and due to its motion. The next thing we're going to take a look at is thermal energy, and thermal energy is simply the amount of kinetic energy that are within the particles of a substance. So in earlier grades, you learned that all material is made out of particles. And when those particles are heated up, they start to move more rapidly. So let's take an example with our popsicles that we have here. So how do you think or compare the thermal energy of these two popsicles? So let's take a look first at our frozen popsicle. So our frozen popsicle has less thermal energy compared to our warm popsicle. That is because when things are solid or when they're cold, those particles that make up this popsicle are moving very slow. So because they're not moving fast, they have slow or less thermal energy. So let's take a look at our little example here. So our frozen popsicle is made of slow moving particles, and then that gives us our solid. Our room temperature popsicle is consisted of faster moving particles because it's warmer, and that gives us our liquid. So the movement and the speed of particles within an object gives us our solids, our liquids, or our gases. Now let's look at some methods of heat transfer. And heat typically moves from warmer objects to cooler objects. So our first example of heat transfer is probably our easiest to remember, and that is simply conduction. So conduction is heat transfer by touching. So for example, I have a color changing board here. I have body heat. Everyone releases body heat. So I'm going to use my body heat. I'm going to transfer that body heat to this color changing board, and you should be able to see my handprint. Now earlier my hand was rather cool, and it didn't leave much of an imprint, but you can kind of see my palm here. Let me try it again and see if we get a better result. So we can kind of see a little bit there. So conduction is just the transfer of heat by touching. Our next example of heat transfer is through convection. And the easiest example for convection, think of your lava lamps. So with convection, there's actually a bulb inside the lava lamp. That bulb is giving off heat. When fluids or gases get hot, they tend to rise to the top because they become less dense. When they rise, they cool off because they're further from the heat source. As they cool off, they become more dense and they start to sink. and that creates the movement in a lava lamp. It's just that continuous cycle of cooling and heating that creates that movement. So that's convection, and convection is responsible for our hurricanes over our oceans. Another example of heat transfer is through radiation, and we have an example over here. Now, the most common method or example of radiation is when we feel the heat energy from our sun. So another example that we have here at the Environmental Center are we have these heat lamps. So I can stick my hand underneath the heat lamp and I can feel the heat. I'm not actually touching the heat lamp itself, but through the process of radiation, I can feel that heat radiating from the heat lamp. And that's very important because a lot of our animals, our cold-blooded animals especially, depend on heat for their survival. So I have an example of one of them here, and this is Spike. He is a bearded dragon. He is cold-blooded, and because he's cold-blooded, his body is not that great at maintaining a constant body temperature. So when he feels cold, he's going to need a heat lamp. Since he's a pet, he's going to need a heat lamp to help him. Oh, and he just jumped off. He's going to need a heat lamp to help him stay warm. And we're going to go ahead and put him back because he's getting a little frisky. But those are the three main ways that heat can be transferred: through conduction or touching, through convection, and through radiation. And before we go, I have a quick reflection question for you guys. I want you guys to think about, in what ways do you use mechanical and thermal energy? So think about the things that you've done so far this morning. How have you used mechanical and thermal energy? And we're going to go ahead and give it back to Mr. Broughton to answer any questions.
Thank you, Ms. Ramirez. That was fun to watch. That little guy is frisky today. The question that came in was, what are all the different kinds of energy? And there are really lots of different forms of energy, but the main ones that you've got to know for fourth grade are mechanical and thermal. So you just saw Mr. Ramirez exploring those. And then there's also light and sound energy. You're about to see that with Miss Nash. Then there's also electrical energy that you're going to see at the end. And those are the main ones, but you did see Mr. Ramirez also mention solar, which is light and heat, but when it comes from the sun, we call it solar. Another question that came in was, can mechanical energy convert to thermal energy? And yes, it can. Your body is a good example of that. If you move around, that's mechanical energy, but when you move around, you also get hot and you start producing more thermal energy. So that's why we're warm-blooded. You can warm up that way. A cold-blooded animal cannot, like Spike that you just saw there. All right, now let's get into light and sound energy with Miss Nash.
Welcome to my classroom. So today we're talking about sound and light. And if you can see me and hear me, then you've got it. Sound is energy we hear, and light is energy we can see. So we humans are pretty good at hearing. We have a pretty good range of hearing, and we have really good eyesight, particularly color vision and acuity. The ability to see details, why we can read. Okay. So we hear because we have a tiny drum inside our ear. I have a big drum here, and this skin vibrates inside your ear. There's a tiny drum that vibrates when the sound waves hit it. Our eyes have lenses inside that the light goes in and it bounces around, and we see color. So we are really good at seeing, but some of our other friends have the ability to see things that we can't see. They can hear what to us is inaudible. They can see what to us is invisible. Pretty amazing. So these kind of superpowers help them survive. So we're going to see some of our friends and think about how that helps them survive. Because whenever an animal has an ability like that, it's a way to help it survive. So let's see if we can go to our pictures here. Here we go. And let's start at the beginning again. I hope, I'm at the end. Well, let's scoot on back to beginning. I forgot to start over again. There. Keep going, go. Yeah. Okay, let's start with light, with sound. There's sound, light. So the visible spectrum, that's that rainbow. Those are the colors we can see, the light we can see. So the white light is actually made up of all those different colors. But below that, last one, red, the slowest wavelength that we can see, there's what we call infrared. And above the violet, the last one we can see, the faster wave, there's ultraviolet that we can't see, but some other animals can. So let's start with the infrared. And you see the copperhead here is a pit viper. And along with other pit vipers and a few of the boas, they have the ability to see things that we can't. That pit there is a sensory device that allows us to see like what we can see with our night vision goggles, which is basically the heat given off by other animals. That helps them hunt. Here's another hunter who's using the same ability, a tiger mosquito. We have these around, big ones, and he's chowing down there. But that helps them find warm-blooded for animals. Another one that was interesting is the goldfish, a kind of carp that tend to live in kind of muddy water in the wild. And maybe that ability to see in that infrared helps them find things in the muddy water. And a bullfrog, so maybe that ability helps them escape from predators. And then here we are with our kind of mid-range vision. We can see a lot of colors, as can our primate friends. Okay, so the monkeys and the apes also have really good color vision. Not all animals do, but the primates, in other words, monkeys and apes, and the birds in particular have really good color vision. And that helps us because like this spider monkey can recognize that this fruit is now ready to eat. So we can see that a red apple is also ready to eat. The hummingbird can see red, and those red flowers are saying, here, here's some yummy, yummy nectar to the hummingbird. But now in the ultraviolet, the higher things that we can't see, it's higher wavelengths, the insects don't see red very well. So the bee, for instance, can't see that red flower that the hummingbird can. Because they can see other markings, like flowers turns out, have a lot of ultraviolet markings on them that tell bees, like this flower, if we looked at it, it would just look yellow, all yellow. But when the bee looks at it, they see that blue ring around, and that says, here it is, come and get it. Another one that was interesting to me was that the reindeer, the caribou, can also detect ultraviolet radiation or light, and they use that to find lichen, the little tiny things that they eat up there in the snowy tundra. And it turns out that urine also leaves trails of ultraviolet radiation around that some animals can see to hunt, like a hawk. You can see the trail that the little mouse left behind. And maybe the little mouse can also see that to try to find his friends. Now for sound, again, we have our field, our auditory field, what we can hear. And then there are other sounds that we can't. They're either too low or too high for our ears to detect. So in the infrasound, that means a really low sound, that goes really well through the ground. So the solids like the earth, the air, and the water all conduct sound. And actually, both solid and liquid water conduct sound better than air. So the elephants can hear other elephants miles and miles away through the earth. There they are with those giant ears. And here's a little friend that also can hear those infrasounds, a little low one, a little mole. So he's got teensy weensy eyes he can barely see, but he can hear things through the earth. Maybe other moles coming, or maybe dinner. And here we are again with our kind of mid-range hearing. And then above our hearing, we've got our friends, the dog family, a little fox with those big ears that can move kind of independently to focus in on sound. And here's one with the biggest ears of all, the fennec. They're gigantic ears, and they're teensy, weensy little foxes. But look at those giant ears. They hunt insects, I think, mostly. And then a bobcat, they again has pretty good sized ears. And then one with gigantic ears, okay, that can hear little tiny mice under the grass. And of course, bats can hear super high pitched sounds that we can't hear. They use that sonar to bounce sound waves off their prey. Dolphins do the same thing with sonar in the water, and they bounce sound waves off things underwater, and they can hear the sound waves come back to them, and they can find their prey, fish. And the great whales also sing, and that sound will go hundreds of miles through the water to the other whales that can hear them. Okay, I'm going to stop sharing now, and back to me. Hang on, there we go, and let's see. No. Okay, so am I back again? So here we are. So there's lots of fun things to learn about the way other animals see, and to think about how color can be a signal to other animals. So again, birds and primates have really good color vision, and so sometimes color can be a warning. Okay, it can also be a signal that here I am, I'm the really prettiest one of all. So interesting thing to discover and explore and learn more about. So if you have any questions, I'm going to turn it over to Mr. Broughton for any questions.
Thank you, Ms. Nash. The question that came in is, which moves faster, light or sound? Light moves faster than sound. Sound can move about 340 meters per second through the air. It moves even faster and farther through the water, like Ms. Nash said, and it's even faster through steel. But even through steel, it's not nearly as fast as light. Light travels at about 300 million meters per second. So it's quite a bit faster than sound energy, but they both do move. And we saw how people use those forms of energy, and animals use those forms of energy every day to live. All right, now we're going to move on to conductors and insulators with Mrs. Fuller.
Good morning, boys and girls. In this segment, we're going to be talking about conduction and insulation. And conduction is to transmit directly heat or electricity along a medium without the physical movement of the medium. And you might say, well, what are some things that will conduct electricity? Well, primarily metals. Metals do an excellent job of transmitting electricity. And also salt water, water from the sea, because of the ions in the water, the salt ions. So that's why the lifeguard tells you to get out of the water when you're at the seashore, when there's a storm coming up and they make everyone get out. That's the reason why. It's because the lightning, which is pure electricity, will travel very quickly through salt water. So when we think about the different kinds of metals, some are better in conductors than others. Gold is the best, but it's prohibitively expensive. Just about the only place that you're going to see gold being used as a conductor is going to be on a circuit board. And that's because they're small and uses a very small amount of gold. Another metal that does a good job of conducting electricity is silver, but it is also very, very expensive if you've ever tried to buy silver jewelry or silverware. Now, silver does have a lot of other really interesting properties, but for the sake of just talking about conduction, the type of metal that we use in the wires that go into our buildings that carry the electricity for us to use is primarily copper. Now I have some wires here, This particular one right here carries the signal from the cable TV. And it's copper right in the middle, has a big copper wire right there in the middle. I don't know if you can see that or not. But that's going to carry the signal. Around it is an insulator. Can you see that white stuff around it? That white stuff is an insulation. And then around that, you see a woven, very tiny wire that's silver in color. That is aluminum. Aluminum is a good conductor. It's adequate conductor of electricity, but it has a tendency to oxidize and short out. So they made an attempt during the 1960s to wire houses with aluminum wiring, thinking because it's so much lighter and so much cheaper than copper that it would do a good job. But unfortunately, because of the oxidation issues, it would spark fires. So they had to stop using that. So in this particular case, it's not carrying the images, it's not carrying the message, it's being used as a ground wire. But in the center around the copper wire, and then on the outside is this thick PVC plastic. It's very pliable, that's an insulator. Now the insulator, let me get my insulator word here. Insulation means creating a barrier between one thing and another. So what you're being insulated against here is being shocked, because the copper wire that comes in our house carries about 240 volts. It's very strong and would electrocute you. So it's very important that we have these insulators, insulating materials on the outside of the wire. Now, some good insulators for electricity are rubber and glass. If you look on a utility pole, very often at the top, you'll see a glass or a ceramic device that the wire runs right beside. Those are called insulators, and it's just to keep the electricity from grounding on the pole or grounding on us. Oil, diamonds, and distilled water. Distilled water doesn't have any ions in it, so it's a good insulator. Salt water is a terrible insulator. It's actually a very good conductor. So those things are not the same. Okay, let's talk a little bit about conduction and heat. Now, just like with electricity, some really good conductors are metals. Silver, copper, aluminum, brass, iron, lead, stainless steel. All of those things do a good job of conducting heat. Well, what are some good insulators? Well, some good insulators for heat are a vacuum, air, styrofoam, body fat, cork, water, glass. Let's talk about a couple of those real quick. Let's talk about styrofoam. This is not good for the environment because when it breaks down, it rises and does damage to the ozone layer, which protects us from ultraviolet radiation. But we use a lot of it nevertheless, and it's an excellent insulator for heat and cold. It's what our little ice chests are made out of. Another one, body fat. If you think about the whales or the seals at the poles, they have a tremendous amount of blubber, which is body fat, and it insulates their bodies against the chill of the ocean water at the poles. Another one, oh, let me show you this. When you take your bagel bites or your little mini pizzas out of the oven, this is an aluminum pan. It's going to be real hot. It's going to be 400 degrees. You can't pick it up with your bare hand. It would burn you. So we use these oven mitts, which are essentially cotton and fabric quilted together to protect us from that kind of heat. We also have on the ends of our serving devices. This is a ladle. It's made of stainless steel. It transmits, it conducts heat very well. But we have some sort of thick, very hard, matte plastic up here. It acts as a handle, but it also insulates our hands from the heat from the shaft of the ladle. Now, this fell out of the ceiling in my closet here in my classroom. Look how thick, it's about 6 inches thick. Well, that's an insulator that keeps the air conditioning from leaving the building and the heat from leaving the building, and it does a good job. But we have another insulator called aerogel, and this is gonna be the insulator of the future. This is what NASA uses on a lot of their devices that they send into outer space. One of the Mars rovers has aerogel all around the electronics box on the Mars rover. The little exploratory ship, Stardust, the one that's out to gather stardust, the way it collects stardust and also particles from comets is with aerogel. Aerogel is 99.8% air. It has a very, very tiny little structure. It can be made of carbon or little things like that, but it has outstanding insulating properties for not just heat, but also things like auditory insulation, acoustical, optical, electronic. I mean, it really does a lot. So anyway, keep your eyes and ears open about aerogel. It's extraordinarily expensive, but as it becomes more popular, hopefully the price will fall and we'll have more of an opportunity to purchase it for our houses. That's all I have about conduction and insulation. I'll turn it to Mr. Broughton. Thank you.
Thank you, Mrs. Fuller. The question that came up was, do animals have insulation? And yes, they do. There are animals that live in the Arctic, like a walrus that has a thick layer of blubber, which insulates its body from the cold and helps keep it warm. So there are animals that use insulation as well. Another question that came in was, is a wire safe to touch? If you don't know if it's safe to touch, then do not touch that wire because it might not be safe to touch. So if you're not sure about something, leave it alone and get an adult to help you. All right, now we're going to move on to electrical circuits with Mr. Monroe.
Good morning, students. My name is Mr. Monroe, and my part of your virtual field trip today is to, we're going to come together and look at how electricity travels in a closed path that we call it a circuit. So there are a variety of circuits, but the one that we're going to be working with today that I'm going to demo is a very simple closed, or what we call a complete circuit. Now, there are several materials that are going to be involved. For the electrical energy source, we're going to be using a D-cell battery with somewhere around 1.5 volts. On one of the circuit boards, we're going to be using a very tiny light bulb. And then you heard Ms. Fuller talk about insulation and the best conductors. We're going to be using a piece of, or several pieces of, copper wire that does have an insulation around it. Now, the first circuit board that I'm going to get up is a very simple one. As you can see right here, there's our D-cell battery. Then we have on the negative part, we've got this wire running here to the light bulb. And on the positive part, we've got this wire running here. Of course, the negative part is coming around to this connection on a switch. Now, this particular switch is called a knife switch. You can see the arrows. Now, these arrows I have put here to show you the flow of electricity. The flow of electricity, we call that the electrical current. And what we're dealing with today is a direct current. So when I push the knife switch down, we see that the light bulb lights. So now we have a closed path for the electricity to pass through. If I was to disconnect this from the battery, then this would go off. because it would act like a switch. If I open up the switch, then we have broke the flow of the electrical current, okay? And everything goes off. If I push it down, the flow is once again started. Now let's say, for example, that the light bulb burns out. And I don't know whether you guys realize that that light bulb is also part of the electrical flow, because inside the light bulb, there are two prongs. And those prongs have a little thin piece of wire that's made out of a substance called tungsten. With the friction of the electrical particles, positive and negative, passing through, it heats up that tungsten, and inside the light bulb, there's an inert gas. And so basically, it makes that light bulb glow with a tremendous glow. Now, if that light bulb was to burn out, the flow would be interrupted, okay? It would not continue in that flow that we have going on now in this closed circuit. Now, not only does it work with light, students, but it will also work with devices that create sound. Here I have a circuit board that has a sound apparatus. And again, I have a knife switch. And when I hit the knife switch, hopefully you guys can hear that sound. And you also can see the arrows that indicate the electrical flow through this circuit. Now, this is a very simple circuit. There are some circuits that maybe a little more difficult. There's one circuit that we call a series circuit, and then another one called a parallel circuit. And of course, boy, I've had an experience with those series circuits simply because long ago, I just loved to put up Christmas lights at Christmas time. And long ago, the lights that were sold, sometimes they would give you a headache trying to figure out what was wrong with them, because they were actually part of what we call a series circuit. That meant that if one of the light bulbs burned out, none of the light bulbs after that would work. So it was a big problem going around trying to figure out which one of those little tiny light bulbs had burned out in that series circuit. For example, are these lights on this series, are they a parallel circuit? Well, with a parallel circuit, it would continue. But look at this. That light bulb is lit, that was lit, that was lit, that was lit, this one's out. So which one of these would you think this would be? Would this be a complete circuit? No. Would it be a series circuit? No, because we still got light bulbs that are on each side of this still lit. So most likely this is a parallel circuit. So there are a variety of circuits. And students, what I hope has happened for you today is that with creating these little simple circuit boards here, you have learned a little bit about how electricity can travel in a closed circuit. If you have any questions, I'm going to turn it back over to Mr. Broughton, and maybe he'll be able to answer those questions for you. And you guys have a good day today. All right, Mr. Broughton.
Thank you, Mr. Monroe. One of the questions that came in was, can a circuit create other forms of energy besides just light and sound? And yes, it can. They can create mechanical energy. There are little motors, like the types of motors that are in remote control cars, that you can put into a circuit, and once the current passes through that motor, it will make it turn around, and that is mechanical energy. So it can produce light, sound, and mechanical energy. Really, a circuit can produce every kind of energy that there is. I'm going to share my screen because one more question came in was, how does a light bulb burn out? And let me show you a picture of a light bulb here. There it is. And you can see that the light bulb has metal right here that helps conduct some electricity, and then it's covered up by this. Let me hide this. Maybe that'll work. There we go. There's also one more point down here that kind conducts electricity. And then that electricity will flow through this wire. And if I zoom in here, you can see this is kind of it looks like a spring or a coiled wire. That is the filament. And that oftentimes gets too hot and eventually gets old and breaks. And once that metal wire breaks, then the light bulb is burned out, we say. So there you can see what the filament, but if it's not burnt out, the electricity will flow through here, down here, and back out the light bulb to keep the electrons flowing and the path closed so that the light bulb stays on if it's not burnt out. All right, let's do a quick recap of what we did today. So let me share my screen with you here, or I'll share a new slide. And today we explored forms of energy. During this virtual field trip, students differentiated among forms of energy. We also differentiated between conductors and insulators of thermal and electric energy. And we observed that electricity travels in a closed path, creating an electrical circuit. So we started off today by exploring mechanical and thermal energy with Ms. Ramirez. Next, we explored light and sound energy with Ms. Nash. Then we explored conductors and insulators with Mrs. Fuller. And you just saw Mr. Monroe using electric circuits to make a light bulb come on and make a sound. Thank you so much for joining us this morning. We appreciate you taking the time to visit us virtually and learn about forms of energy with us. We would love to know what you thought about this morning's virtual field trip. And you can let us know by going to www.tiny.cc/EEC feedback and filling out a short feedback form. It takes 1 or maybe 2 minutes at the most to fill out to let us know what you thought about today's trip. We use your comments and suggestions to improve what we do, and we hope to see you again in about 3 weeks. Thank you and have a great rest of your day. Goodbye.